like to move to our next speaker. Our next speaker is Abhay Shankar Shastry. Abhay Shankar Shastry completed his PhD in physics from University of Arizona, advised by Professor Charles S. Stafford. His doctoral work focused on developing thermodynamic theory for quantum systems far from equilibrium. He established rigorous notions of thermodynamic variables by relying upon local measurements made by probe for non-equilibrium systems in a steady state. He proved existence and uniqueness theorems for temperature and voltage measurements for quantum fermion systems arbitrarily far from equilibrium, with arbitrary interactions within the quantum system. Later, he spent a year as a postdoc in the Department of Chemistry at Toronto University, where he was advised by Professor Vera Segal. He has worked with experimentalists at the Weizmann Institute to understand 1/f noise, which is trigger noise in single molecular junctions. Presently, Abhay is a postdoc in the Department of Computer Science and Automation and is working on topics in quantum machine learning in the group of Professor Chiranjeev Bhattacharya. With that, I would like to invite Abhay to present a talk on ensuring robustness in quantum kernel methods. Abhay, you may please share your screen. Abhay, I think you are muted. Yeah, I can see your screen, but Abhay, I think you are muted.
Oh, hi, thank you. Thank you, Asif, for that very nice introduction. It's been really great listening to all of these talks, and thank you for organizing this. Yeah, especially to hear talks from our colleagues in the industry, it's been very nice. So my talk is slightly on the technical side, so feel free to ask me, stop the talk and ask me if you have any questions. So is this visible?
Yes, it's visible.
Okay, so I'm going to talk about ensuring robustness in quantum kernel classifiers. One of the big machine learning areas in which quantum computing is thought to have an advantage is this in the supervised paradigm, where you have kernel methods. This is before your whole deep learning era came in. This was a very famous paradigm in classical machine learning. Now, one issue has been that quantum kernels are measured using quantum circuits, and this means they are inherently noisy. So I'm going to talk about classical methods to sort of mitigate this noise. That is, and ensure robustness essentially. So that is going to be the topic. So this work is in collaboration with Abhijit, who is at Los Alamos National Lab, and Apurva Patel and Chiranjeev Bhattacharya, who are professors at the Indian Institute of Science. With that, I will like to proceed. So now there is a viewpoint that quantum supervised learning is essentially kernel methods. That is, all of your architectures like parameterized quantum machines, parameterized quantum circuits, and so on, they can all be mapped into a kernel method. So this is a very nice archive paper, preprint. So you can read more about this in that. And secondly, the setup. What is the setup? It's a hybrid classical quantum setup where the optimization problem is solved on a classical machine, but the kernel is evaluated on a quantum machine. I'll come to the optimization problem. All of these methods in ML require solving an optimization problem. So that will be done on a classical machine. So now, what are kernels? So suppose you have this. Is my mouse pointer visible?
I think, yeah, it's visible.
I think okay. You are not sharing the side slope. It is still the first slide only.
Oh.
Yeah.
That is strange.
Now
Thanks for.
Yeah.
Thanks for telling me.
Content kernels.
Okay, maybe I should share the whole window rather than. So perhaps. So okay, this was the first slide. Is this visible? The first
No,
slide?
no, you're not sharing screen. Could you please reshare? Yeah, now it's visible. Yeah. Yeah.
Is it working?
Yeah, it's working now. Yeah. Thank you.
Okay, thanks for that. Yeah, a good time to catch that. Here, suppose you have two classes, these blue points and green points. Clearly, they can be separated by a straight line. So these are called linearly separable data classes. So now, your problem in this classical ML is to draw a line and an optimal line which separates these two classes. So this is known as the optimal margin separating hyperplane, this red colored. And this is classical support vector machines. So essentially you would solve for the parameters W and B to find that line. And it is a quadratic optimization problem that comes about. And what are kernels? Most data points are not like this. They are spread out, they're highly nonlinear classes. So kernels come in here, they're very handy. Suppose you have points like this, and if you were to draw a circle, it would get separated. And circle is not a straight line. So you can imagine embedding these points, all of them, onto the surface of a cone. And on this cone, if I were to draw a hyperplane, which is a straight line, then they can be separated. So the idea is that you can draw highly nonlinear boundaries by embedding your data into higher dimensional space. And the main crux of the kernel method is that you only need to efficiently compute the inner products between the embeddings. So you embed your data vectors, and you need an efficient algorithm to compute these inner products. So that inner product is essentially the kernel. So this is the background. Now, what are quantum kernels? Quantum kernels are where you embed these data points onto a state in the Hilbert space. And your inner product will be defined by a Hilbert-Schmidt inner product between the two states. So this essentially amounts to a transition probability between these two states. And how do you measure that? You create a circuit and you try to infer this quantity. So now, so if you were to write down the density matrices themselves, it becomes computationally intractable. The idea is this quantity can be computed efficiently. You don't have to exactly know what these states are. So, so it becomes a natural candidate to extend kernel methods into the quantum domain. So, and there are two circuits which can both give you this kernel value. We'll talk about them. And what kind of kernels can be realized in quantum circuits? These are the different kernels. And amongst this Gaussian kernel is a rather popular kernel in classical machine learning. And that can be seen as coherent state encoding. Yeah, so now what is the advantage? I mean, there is some talk of quantum advantage. This is not why we are exploring it. But some work has gone in this direction. Essentially, you need some unitary which is conjectured to be hard to simulate classically. So then you can imagine that these kernels will be hard to compute classically, but quantum mechanically you can do it. What is the data set for which it is useful and all of that? It's not very clear. The answers are not very clear. And another conjecture has been, suppose I make a synthetic data set which uses the discrete logarithm to label the discrete log function to label these classes in the data set, then clearly you cannot have a classical kernel represented, because that would amount to solving the discrete log problem, which is conjectured to be hard classically. Okay, so what? I can do these things, but quantum computers are highly noisy. Tell me how to deal with that first. Like all of this talk is nice, but we need to deal with noise. There are two types of noise. There's a fundamental quantum measurement noise, and there's a device noise, which this can be mitigated or corrected, but you can't do anything about it. Even this quantum measurement noise, you have to live with it, even in the era of fault-tolerant computing. So it's very important to understand how this affects the performance of this classifier. So there are two circuits which you can use to calculate this kernel. One is to take the feature map and use these two unitary gates sequentially, and then you measure on these n qubits. The other one is known as a swap circuit, where you embed one vector here, another vector here, and then you use this swap operation, and you can do a measurement on this ancillary qubit up here. That will give you, from that you can infer this kernel value. So mainly you have to, in any case, you have to infer from measurements. The kernel value is always inferred from measurements. So suppose I do some 1000 measurements, and I get the state to be 0 most of the time, 750 times, and 250 times I have state 1. So I will infer the kernel value as the expected value here. So it will be 0.25. But with some error, right? I have done it 1000 times. If I do it infinitely many times, I'm sure to get the correct kernel value. Almost surely it will go to that mean value. But how many measurements should we use? That is a very pertinent question. So there is no clear-cut answer in the literature. So when this first sort of one of the very early kernel papers was by the IBM group, it was published in Nature 2019. Here they used 50,000 measurements and used their own 5-qubit quantum machine to evaluate kernels. Later, some other people used 8-bit IBM Q machine, used 2000 measurements, so on. There is no clear standard. So we want to establish a standard for how many measurements you need. So why is this important? If you look at this paper, the second paper here, you can see the reported accuracies on some classification task that they have. You can see that the range of the observed accuracies is very large. This implies unreliable classification. So every time I ask a question, what is this point? Is it a +1 or a -1? Is its label +1 or a -1? Or some image, is it a cat or a dog? If I ask, half the times if you tell me it's a cat, half the times if you tell me it's a dog, then you can say that the accuracy is bad. But if given the same data point, each time you are coming back with a different answer, that means your answer is not reliable. It's not that the accuracy or the data set is bad. That is also true in this particular case. But for the same figure on a Monday, if you ask, it is saying cat. Tuesday, it is saying dog. So this is highly unreliable classification. So it is happening due to the underlying noise in the circuit. So first we introduce and this problem has not been studied from the lens of reliability or robustness, which is a very important concept in classical machine learning. So we introduce the notion of reliability. This quantifies the probability with which a classifier may go wrong, and we want this probability to be very small. That is the message. And so these are some of the results. One can see, one can prove these things using simple bounds in probability theory, Chernoff bounds. You can show that if I want to measure the kernel up to a precision epsilon, I will need order 1 by epsilon square number of measurements. And if I want to do it for a data set of size m, then I will scale as I'll scale quadratically. So, and total measurements will scale as m to the 4. And an important point was made here in this NeurIPS 2021 paper, that if the precision needed is exponential, all talk of quantum advantage is not very useful. Now we ask these questions: is there a better metric to measure the reliability of a quantum classifier? Can we obtain a better scaling for this n? And can we reduce the number of measurements needed without sacrificing the robustness or reliability of this classifier? So our approach is you only need good classification and not precise kernel evaluation. So this helps out a lot. I don't have to precisely tell you what the kernel value is, as long as you're on the correct side of the decision boundary. So that is what we want to work with. So the relevant parameter becomes the margin of classification instead of the precision epsilon, which can be vanishingly small. But a margin for a well-defined kernel classifier, it is of order 1. So there itself you see a lot of improvement in the bound. So, and then we will introduce a chance constraint optimization approach, which will result in robust classifiers with requiring even smaller number of measurements than the one set by this bound. Now, yeah, so I'm just stating these results in a more mathematically precise language here. Precise kernel evaluation, you can see that it scales as 1 over epsilon square, and with probability here, you can, what is this delta? Delta is ensuring that equation 109, your norm of your difference in norm of the kernel that you infer and the ideal kernel, if that is to be bounded by epsilon, and I want to satisfy this with high probability, with at least 1 minus delta, then this is the number of measurements I will need. However, if you turn to the argument that, hey, I don't need to measure it very precisely, I just need to be on the correct side of this margin, then one simple thing you notice is as I get closer to the decision boundary, I will need more number of measurements. So if your point is on the boundary, then actually you will need infinite number of measurements to tell it apart. So first, you have to understand that you should design a good kernel which can separate these data points with a reasonable margin. And that is not answered by this analysis. I'm just giving you a framework to analyze this. We are not answering the question of how to design that kernel. That's a separate question. Yeah, if you want to bound the errors in this quantum kernel classifier up to a you want to make it better than the gamma margin error of an ideal classifier that is on the right hand side here, then you need these many measurements. So you can see that it scales inverse quadratically with gamma, and you improve the bound on the data set exponentially, in fact. So there is no m coming in outside the log. So from m log m, I have taken it to just log m. So that is also a very good, that kind of exponentially improves the bound. Now, the main take-home message in this paper is you want to do the optimization problem with high probability. So I told you there is an optimization problem that you need to solve, and you're working with noisy kernels K. So now I want to minimize that objective, but with high probability. I can't always guarantee the minimization of that. So I will say with high probability, we will minimize this objective. This objective J is the objective of the your support vector machine. So now this is generally classically also intractable. So you have to make convex approximations, what are known as convex approximations to this chance constraint program. So this equation here is the chance constraint. That is, with 1 minus delta chance, I want to satisfy this inequality. So when you do convex relaxations, you will come up with what is known as a second order cone program. It's a type of convex optimization problem, but it is not as easy as a quadratic optimization problem to solve. So some more classical resources you will spend, but you get a huge saving in quantum resources. That is the kind of trade-off that you see in this kind of problem. So how does this work in practice? Some toy data sets we have taken. So you can see that using this short, frugal, and robust method, which I'm labeling as shofar here. This is the shofar program, short, frugal, and robust program. If you use that, then you can save over 90% in some cases on the number of shots that you need using a nominal SVM. And we've also analyzed this, the performance of this program with respect to other device noises, and it performs very well. It is quite robust to other device noises, such as we used a depolarizing noise model. Thank you. With that, that is the message of this paper. You can use classical optimization techniques to bring down your use of quantum resources. Thank you very much for listening, and thanks for this opportunity to speak.